Okay, did you all get the notice about the postponed exam? You happy about it? Okay, I knew it. It's rare that somebody will complain about something postponed. All right. The purpose for that was really to be able to assign another homework so you practice more. And by the way, if you're not, if you're working on the project for the lab, right, Python lab, and if you feel you need more practice problems on the material you're covering, the textbook that I recommended, but I didn't require, is a good resource for that. Because at the end of every chapter, they have a bunch of problems. And some of them are basic problems that are actually worked out. All right? So there's no shortage of practice problems in that book. And it's in the reserve in the engineering library. You can check it out for 2 hours. I don't think you can leave the library with it, but you can actually, I don't know how it works, but it's on 2-hour loan. Okay? All right, so we'll talk a little about body plots today. You may have been introduced to some degree in 16b, but it's good to go over it again. I have a witness. Alex was a GSI for 16b, so I brought him to take the witness stand if anybody says, oh, no, we don't see. What is Bodhi? All right, so Bodhi was one of those guys who worked at Bell Labs. And so the Bodhi plots are basically approximations to the frequency response of a transfer function, right? So why do we need an approximation? Back in the day when those were introduced, it was probably a computational tool to, approximately draw these plots. These days you can use Python, MATLAB, whatever you have, to plot them accurately. But nevertheless, the Bodhi plots give us a lot of intuition without having to type in commands and see. So you should be able to, in your mind, relate poles and zeros of a transfer function to its frequency response without moving a finger. And that's what the Bodhi plots help you with. So key features of Bodhi plots is they are straight line approximations. So they look nice and straight. Okay. The second point is that they are given on a log-log scale if you are looking at the magnitude of the frequency response. Why log scale? Log scale has several advantages. It allows you to compress a lot of information into one plot, right? Because you can cover many orders of magnitude in one plot when you plot against the logarithm of something. The other reason why we like these log plots here is that they enable these straight line approximations. Okay, so the actual frequency response plots do look sort of linear or piecewise linear when you plot them on a log scale, and that's what the Bodhi plots leverage. Okay, so that's why we use logarithmic scales. So I'll go through a couple of examples to illustrate the main ideas. So the first example is a system with a simple pole. All right, h of s 1 over tau s plus 1. All right, where's the pole? Tau is a coefficient. Where's the pole? Pole is at s equals negative 1 over tau, right? I could have written 1 over s plus a. I guess that would have been simpler. Then I wouldn't ask you where's the pole. It would be just negative a. But the reason for writing it in this form is that if I set s equal to 0 to find the DC gain. Remember the DC gain? It's the value of the frequency response when the frequency is 0. Or the value of the transfer function when s is equal to 0. Same thing, right? So when you evaluate this guy at s equal to 0, you get 1. So the advantage of this form, writing it in this form, 1 over tau s plus 1, is that it allows you to display the DC gain explicitly. In this case, the DC gain is what you see here. It's 1. Okay? We'll look at different DC gains shortly in other examples. All right, so we want to make a plot of the frequency response h of j omega which is 1 over 1 plus j omega tau, right? I just switched the order of tau s and 1, substituted j omega for s. And there are two things, of course, we are interested in. First, we're interested in the magnitude of this. And, of course, the magnitude of that is 1 over the magnitude of this, right? And the magnitude of the denominator is simply 1, that comes from the real part, omega tau squared, that comes from the imaginary part, and you take the square root. Okay? That's because 1 plus j omega tau looks like this. Omega tau j, right? So the distance to the origin is the magnitude, and it's equal to that. All right. So therefore, we have 1 over this expression for the frequency response. We already know that. There's nothing new here. What we are doing in Bode plots is we're kind of approximating this, right? So the first thing we'll note is that 1 plus omega tau squared is going to look like, can be approximated with omega tau squared if omega tau is much, much bigger than 1. Clearly, because then 1 is nothing compared to omega tau squared, right? And similarly, if omega tau is much smaller than 1, then this is the omega tau squared term is too small compared to 1, so then we can approximate it as 1. Okay, so the main premise of the Bode plots is to use this approximation. So we can then say that the magnitude, h of j omega, is approximately equal to 1 over omega tau when omega tau is a lot bigger than 1, and 1 when omega tau is a lot smaller than 1. All right? Do we agree with this? Yes? Okay. So, but I said we're going to use logarithmic scales. So I'm not just going to plot magnitude of h versus omega. Clearly, there is nothing linear or straight line looking there. Right? It's 1 over omega. It will go like this. So, but if I look at the logarithm of this, and that's what the so-called decibel scale does. So, you've heard that expression before, decibels? All right. So, the decibel scale, and it's abbreviated as dB. So, converts the magnitude h to its logarithmic value, to its log in base 10, to its log 10 value, and multiplies by 20, the magic number. Why 20? I think this has its roots in circuit theory. People initially want to plot the voltage gain, that was to be the transfer function. And for that they use 10, okay? And then they want to plot the power, which includes voltage square, and that created a 20. So don't question where the 20 comes from, just accept it as a fact. So instead of plotting the norm, the magnitude of h of j omega, is there a question or comment? Okay. We are going to plot 20 times log 10 of that. All right? So how can I approximate this if I go back to what I had here? When omega tau is much bigger than 1, when we're in this regime, we're going to be looking at the logarithm of that. So 1 over something, when you take the logarithm, it's going to be negative logarithm of what's in the denominator, right? So it is going to be negative 20 times log 10 omega tau. when omega tau is a lot bigger than 1. And it's going to be 20 times 20, in fact, doesn't matter now, logarithm of 1 when omega tau. What is logarithm of 1? In any base, logarithm of 1 is 0, so it's going to be 0 dBs when omega tau is a lot smaller than 1. All right? So that's basically the approximation. And you can now see that what I have here is looking linear in log omega, right? You can actually separate tau out of there, so you can rewrite this expression here as 20 log tan omega, and again another 20 log tan tau. Right? Agree? Okay. Now I'm going to do some magic. Oh, not yet. What do you think? Are you impressed? I just made this in 1 millisecond. You didn't even see me drawing it. All right, so this is going to be omega, but we are plotting against logarithm of omega. So what we're going to do is we're going to call this point 1 over tau. Okay? This is 10 over tau, because when I actually plot the, although I'm saying omega here, I'm really thinking of the logarithm of that. So because then between 1 and 10 and 100 of the same number, you're going to go linearly between those, right? Each one gives you 1. So this distance between them is called a decade, if you have not heard that expression before. So let me also mark this point. All right? So instead of plotting against the linear omega axis, we just put the omega in this logarithmic scale. All right? So that way, you know, each one is a multiplication by 10, really, although they seem to go, you know, in regular intervals. Does that make sense? So, you know, going from the first point to the second one, I multiplied by 10, really, and going from the second to the third, I multiplied by another 10. So each one of these intervals is called a decade. Decade because you multiplied by 10, really, to go from one to the other. All right? So essentially, plotting 20 log 10 h omega on this scale amounts to plotting this against log 10 omega, right? Now, what is our approximation? Our approximation says when omega tau is a lot smaller than 1, which means that omega is a lot smaller than 1 over tau, that means up to this point, right? Before this point, we're approximating it with 0 dB, which is this point. All right, so this is our first straight line in the approximation. So we have this approximation up to omega equals 1 over tau, right? What happens after 1 over tau? Now we're in this area, right? Or this one, which is written more explicitly. When omega is 1 over tau, this will be log, this term here will be log 1 over tau, which is negative log tau, so they will cancel and they'll be 0, so that's why we have continuity, right? We are still at 0 dB. And then what happens afterwards? When omega goes to 10 over tau, what happens to this term here? What did you say? Minus 20 and plus 20 log 10 tau, right? Because of the tau in the denominator. And that cancels with this guy, right? So you end up with negative 20 here at the end of 1 decade after 1 over tau. Let's mark this as negative 20 dB. Okay? So, and as you can see, we are going linear. We depend linearly on log of omega. And at every decade, I'm going to drop by another 20. So the rest of the body plot is a straight line that keeps going down like this. All right? And the slope of this guy is what we call 20 dBs, negative 20 decibels per decade. At the end of 1 decade after 1 over tau, that is at 10 over tau, we reach negative 20. At 100 over tau, we reach negative 40, and so on. Okay, clear? So that's a straight line approximation to the actual frequency response given in the log-log scale. How does it compare to the original one? If I were to draw the original one on top of this approximation, it actually is going to look pretty similar. It is going to look like this. You know, it will be close to 0 dB because the actual frequency response is close to 1 for small frequencies. And then it will go down almost linearly like that, right? So that's why this is a good approximation for small frequencies and large frequencies. The only place where you start looking at bigger errors is exactly at the cutoff frequency, which is 1 over tau, right? So you may wonder what exactly, how much off are we at that point? We know the value of our approximation when omega is 1 over tau. It is 0 dB, right? What is the actual frequency response when omega is 1 over tau? Let's go back. So if omega is 1 over tau, then this is equal to 1. And what is the magnitude of this then? 1 over square root of 2, right? So the actual value here is negative 20 logarithm of, no, positive 20 because it's in the denominator, square root of, what am I talking about? Yeah, positive 20 logarithm 1 over square root of 2, right? But you can simplify this because that's the same as negative 20 log square root of 2. And because it's a square root, it's 1/2 log 2. So that's actually negative 10 log 2. So if you look at logarithm of 2, does anybody know? 0.3, okay. I think you somehow know the answer you're going backwards, but anyway. So this is going to look like negative 3. So this error, this is the biggest error you can ever get, and this is negative 3 dB, which in the linear scale means 1 over square root of 2, obviously, rather than 1. Okay? So the error is always smaller than 1. That's as far apart the approximation can grow from the actual frequency response. So it's a pretty decent approximation, right? And it's piecewise linear. That's another good thing about it. All right, makes sense? All right, that was example 1. It was one single pole, right? DC gain equal to 1. Example 2, I'm going to make it a single 0 instead. And we're not going to have to do much work here because it's going to look very much like the pole example. So example 2, we're going to assume we have a single 0, nothing else. So tau s plus 1. All right? So let me call this H2, 2 for example 2. All right? And let's think of H1 in example 1 as 1 over tau s plus 1. Right? So clearly, H2 of j omega is 1 over H1 of j omega. Right? And what does that indicate? It indicates that the magnitude of H2 of j omega is 1 over the magnitude of H1 of j omega. When I take logs, though, you're just going to end up with a negative sign. So it's going to be negative log 10 H1 of j omega. And for that reason, of course, you can multiply both sides by 20. for that reason, I don't need to do all these approximations all over again. It's going to look very similar. Just the sign will flip, right? So, another magic. So now we're looking at the magnitude again. So it's going to, that was 1 over tau, right? 1 over tau. So up to that point, again, it will be 0 dBs. Let's make it more solid. Okay, so 1 over 0 dB up to that point. And then it grows by 20 decibels every decade. So by the time you get here, you're at 20 dBs. And then you reach 40 dB a decade after that, that is here. Okay, so basically this grows linearly afterwards. Okay, makes sense? And of course, if you were to plot the actual frequency response, it would not have a kink like this. It would more smoothly bend over, and you would get 3 dBs of error at omega equals 1 over tau. Right? Same idea, really. All right, so let me add a page before, because I also want to tell you about the phase. So here we only talked about, I'm going back to example 1 now, which is a weird way of doing it, but anyway. So we're looking at example 1. What is the phase of this transfer function? So if you look at the phase of h of j omega, it's the phase, of course, h in that example was 1 over 1 plus j omega tau, right? So therefore, it is negative the phase of what's in the denominator. Okay? So, and of course, that is the angle of this complex number. 1 is the real part, omega tau is the imaginary part. Okay, so we're talking about the angle here with a negative sign. And we know that that's negative tangent inverse omega tau, right? But when you plot it on a logarithmic scale, it's not going to go like a tangent. It will look much more constant. When omega is small, again, much more constant. So at least you can tell me the values. When omega goes to 0, what would that be? 0 degrees. And omega goes to infinity, you'll get 90 degrees. Today I'll call them 90, 100 just to make it more accessible, I guess. So when you plot this on the logarithmic scale, rather than like an inverse tangent, it will actually look more straight, like 0 and 90 degrees. Actually, negative 90 degrees, keep the sign. And more like negative 90 degrees, and a sharp transition in between. So the way the Bode approximation does that is as follows. So until, so wait, what am I doing? So this is 1 over tau, right? That's our cutoff. So this is 1 over tau. This is 0.1 over tau. This is 100 over 10 over tau, 100 over tau, etc. So the approximation is like this. So up until a decade before the cutoff frequency, which is 1 over tau, that is up until 0.1 over tau, we take it to be 0 degrees. Once we've passed a decade from 1 over tau, we approximate it as a straight line at negative 90 degrees. And in between, we draw a straight line. So that straight line drops 45 degrees at every decade. There are only 2 decades, so you end up dropping by 90 degrees. And because it's a straight line, the value at 1 over tau is actually exactly negative 45 degrees. Now, what is the exact value of the phase when omega tau is actually equal to 1? When this is 1. This is 1, and this is also 1, right? So it's actually 45 degrees. So at this point, there's no error. So the true phase plot for the frequency response would look more smooth, of course, than the straight line approximation. It would look more like this. But at this point, it would actually match the Bode approximation. Okay? All right, so that was example 1. Remember, example 2 is very similar. We just have it in the numerator, not the denominator. So given this, you will probably believe if I tell you that H2 of j omega is the negative of H1 of j omega, right? So all you have to do is you go back to this phase plot, change the sign, right? So going from pole to 0 is very easy. You basically change the sign of both the magnitude plot and the phase plot. So instead of going from 0 to 90 over negative 90 over 2 decades, you go from 0 to positive 90 over 2 decades. And at 1 over tau, you reach the value 45 degrees. I'm not going to draw that again because I assume you can imagine flipping this plot relative to the horizontal axis. Yes? Change the sign. Make sense? Are you following? All right. So, and example 3 is going to be extremely straightforward. We are going to take a transfer function that's a constant. Example 3. H of s is a constant gain. There is no pole, no zero, nothing. Just a single gain, constant. And let's assume it's positive. So what would the Bode plot of that look like? So at the top, I'm going to draw the magnitude. At the bottom, I'm going to draw the phase. And hint, they'll look extremely boring. What's the magnitude? 20 log k. Does it change with frequency? No. So that makes our life easier. So whatever k is, it's going to be that. 20 log in basis 10 of the value of k. Okay, obviously it's going to be above the 0 dB line if k is bigger than 1, and if k is smaller than 1, it will be less than 0 dB. What about the phase? It's a real number and positive real number, so its phase is, angle is 0. So 0 degrees. Okay. Okay, so 0 degrees. Now, what if k was negative? So I'm going to remove this assumption. If k was negative, all you'd have to do here is to put an absolute value, right? Because then the magnitude of h is magnitude absolute value of k, right? But what happens to the phase? If k is a negative number, the phase is -180, negative pi, 180, right? So therefore you would select 180 if k is negative. And 0 if k is positive. Okay? So that was straightforward. Nothing really changes with omega. That's why we have these horizontal lines. All right. So what did we talk about so far? 3 examples. First, a single pole. Next, a single zero. And a constant gain. Once we have that, we can actually do pretty much the Bode plot of anything you can imagine. Or, well, there are some exceptions that we can't build out of these 3, but a lot of other things we can. So what if I give you a transfer function of this form? It's too thick. So what if I give you a transfer function that doesn't have just a single pole, a single zero, or a constant gain, but a combination of these, a gain k, and then some zeros, let's say m zeros, at values negative 1 over tau 1 to negative 1 over tau m, and then some poles, and let's say n poles, so that then we would start at tau m plus 1, because we start labeling taus from 1 to m for the zeros, to tau m plus ns plus 1. Right? So what do we do in this case? Now, you now see the role of the k, because when we write things in this form, tau s plus 1, when I set s equal to 0, they become 1. Okay? So anything you write of this form here is going to have a DC gain of 1. A DC gain that is different than 1 would have to be factored out in the form of this k. Right? So therefore, from this very form, it should be clear that h of 0, which is the DC gain, is equal to k. I may not give you transfer functions already put in this form, but you may have to bring it to that form by factoring out the DC gain and writing the poles, each pole and 0, in this form, in this tau form. Right? So then, let's start with the easy case. If we look at the phase of h, it's going to be the phase of k, right, plus the phase of tau I j, how did I write it before? 1 plus j omega tau I, right? So sum of those from I 1 to m. For the zeros, you add those up, right? These angles. And for the poles, you subtract them. That's because, when you're multiplying, dividing complex numbers, their phases add up or subtract, right? Is that clear? I mean, that's one of the first things we discussed when we were reviewing complex numbers. If I have a complex number z that looks like, z1, z2 by z3, then the magnitude of z will be the magnitudes multiplied and divided, whereas the phases will just add and subtract. z2 minus z3. Okay? So basically, we're applying this principle here. So therefore, whatever is in the denominator, we subtract them. So I m plus 1 to m plus n, we're subtracting those phases. Okay, so what's the summary here? That means, if I want to draw the phase, body phase plot for this rather complicated looking transfer function with multiple poles and zeros, it actually is no more complicated than making a body plot for a single pole, single zero, or a constant gain. You just make those plots individually and add them up, or subtract if they were coming from the denominator, right? Okay, so that's very simple. You just add up the plots. Okay, now according to this, magnitude is not so easy. It's not just additive, right? But we have something to our advantage. We are not really plotting the magnitude as it is. We are plotting the logarithm of the magnitude. So if I look at this and ask you, what is the logarithm of z? What is it? Log z1 plus z2 minus log z3. So that makes all the magnitude plot also additive. All right? So both phase and magnitude are obtained by adding simple body plots for a single pole, single zero, or constant gain. Add them up, and you get the body plot for something as complicated as this. All right? So just to put that a little more formally, 20 log 10 h of j omega will be 20 log 10 k plus a sum of terms that come from the zeros 10 1 plus j omega tau. And then the contribution of the poles is to basically subtract similar terms. I want m plus 1 to m plus n, 20 log 10 1 plus j omega tau I. All right, so we have all the expressions we need. The expressions may look ugly, but they say something very simple. To make a body plot for a transfer function with poles and zeros, just make individual plots, add them up. All right, let's see how that works in this example from last time, actually. Example 4. So we have this transfer function with a single pole and a single zero. All right? First thing you should do, if I ask you to draw the body plots rather, because it's both magnitude and phase, right? First thing you should ask yourself is, what is the DC gain? So K, which I call the DC gain, H of 0, is, when you substitute S equals 0, you get 0.1, right? So that means we need to first put this in the form that complies with this form at the top here, right? That means factoring out the DC gain, writing this as 0.1 times, the numerator is already of the form tau S plus 1, tau being 1, right? So I leave that alone. But the denominator is not, so now I put it in this form, 0.1s plus 1. Do you agree the two are the same? All right, so there's a first step where you want to bring the transfer function to this form that displays the DC gain explicitly and puts into this tau S plus 1 form. So, and that's what we've accomplished here. So then the rest is making body plots for the gain, 0 and pole, adding them up. So I'm going to do this for the magnitude. So let's start with what? I don't know. Let's start with the magnitude plot for the gain K, 0.1. What is log 0.1? Negative 1 multiplied by 20, negative 20 dB. So we're basically looking at this example here, right? K being 0.1, this is below 0 dB. It's negative 20 dB. All right, so that's going to be, let's use some colors here. Green maybe for the constant term. So negative 20 dB. Okay, so while I'm at it, I'm going to do something fancy here. Color code everything, all right? And then S plus 1, what's your next favorite color? You have the menu up there. Oh, no, you don't see it. I get to see it. Okay, cool. I like the power. Okay. So let's use orange for that. Orange is one of my favorite colors. So S plus 1. So single 0, right? The magnitude is going to be, oh, I didn't, shoot. Okay, I need to label these. So we go from 0.1, 1, 10, 100. So this is omega in the logarithmic scale. All right, now back to S plus 1. So the critical frequency for that is omega equals 1 because tau is equal to 1, right? The critical frequency is 1 over tau. Tau being 1, it's 1. So that means up until 1, I'm going to be 0 dB. And afterwards, I'm going to increase by 20 dBs per decade because this pertains to the 0, right? All right, that's pretty cool. So this is 0 dB. And finally, we have, let's keep this in blue for the pole. So we have 0.1 S plus 1. Tau is 0.1 for the pole. Therefore, we are looking at the critical frequency is 1 over tau, which is 10, right? That means for the pole up until omega equals 10, we're going to have a straight line at 0 dB. And afterwards, we're going to drop by 20 dBs per decade. All right? Make sense? So this is not the body plot I'm looking at. This is the body plots for the gain, 0, and pole. The actual body plot for this transfer function is going to be a sum of these three. And let's use red for this. So now we're actually plotting 20 log 10 h of j omega. So how do I add them up? Easy. Up until 1, nothing is really happening. So I'm adding 0, 0, and 20, negative 20, right? So they are going to stay at, the sum stays at negative 20. What happens from 1 to 10? I start going up. The orange line wants to move me up by 20 dBs in 1 decade. The blue line is doing nothing, so I go with the orange. So I go from where I am, which is negative 20 dB, to 0 dB, right? And what happens after? Now there's a battle between the orange and the blue. Orange wants to take us up by 20 dBs. Blue wants to pull us by 20 dBs. What do? We don't move. We stay flat. All right, so afterwards, we just decide to stay flat. Okay, so the red curve is the body plot, which we obtain simply from the body plots of the constitutive elements. All right? And then we can do something similar for the phase. Let's do it while we're at it. Phase is actually slightly more interesting, I would say. Okay. All right, so for the phase, we're looking at the gain first, and the gain contributes nothing, right? The gain is positive, so the phase of the positive number is 0, so 0 degrees for the gain. So I don't even need to draw this, but just to be complete. So that's 0 degrees. What about the 0? It's going to contribute eventually an angle of positive or negative? Positive 90 degrees. And we go there gradually, starting at point 1. Starting at point 1, we start going up. And then here onwards, we are at 90 degrees. And in between, we grow linearly. Okay? So that is 90 degrees. Okay, what is left? What is left is the pole. What does the pole contribute? The pole, what color was the pole? Blue. All right, the pole will look, again, it will go from 0 to negative 90, and it will start because so our tau is 0.1. So the critical frequency is 1 over tau, which is 10, right? So that's why it started changing here at 10. So because the center is 10, we start going down at 1 and finish going down to negative 90 at 100. So up until 1, we are flat. And then negative 90, after this. And in between, it drops linearly. Okay? So these are the individual pieces. What we need to do is we need to add them up. And that's done in red. So what do you get when you add them up? start at 0, go with the orange, go to 45, which is midway, stay there, and then go down, and afterwards positive 90 and negative 90 cancel each other, so you stay at 0. All right, so this is negative 90, this is 45 degrees. So you essentially get a bump, all right? You jump from 0 to 45 and come back. Okay, so the phase goes up and comes down. And the magnitude starts at negative 20 dBs, goes to 0 dBs. In the linear scale, negative 20 dB means 0.1, right? So that means the magnitude started at 0.1, went to 10. No, went to 1, 0.1 to 1, right? Because 1 is 0 dB. And the phase started at 0, went to 45, and came back. Let's compare this approximation to what we had last time. So we actually talked about a geometric interpretation of the frequency response. And h of s, s plus 1 by s plus 10 was actually one of our examples. There we were not making accurate or even approximate sketches. We were making very, rough sketches, right? We imagined picking a point on the imaginary axis, j omega, measuring the distance to the pole, measuring the distance to the 0, dividing them to get the magnitude plot, and of course that went from 1 over 10 to 1, right? And then the phase was the angle that you see at the top here, because it's the difference of the two phases. And we realized that that would start at 0, increase, and come back down to 0. So that's how we made these very rough, extremely rough sketches based on geometric intuition. So body plot is a lot more accurate than that, even though it has some approximation errors. It also looks prettier. It is like a straight line plot, because here omega was on a linear scale, whereas when we do body plots, we use logarithmic scales. It's a log-log scale for the magnitude, because we also look at log of the magnitude, right? And it's what you would call a semi-log scale when you look at the phase, because you don't mess with the phase. It's still, degrees, right? You don't look at the logarithm of degrees or anything like that. But the omega is still in a log scale, right? So that's something you sort of saw in 16. Now you've seen it completely. So this was one example of how we could create more complicated things from simpler blocks. What I want to show you next is very simple, so it's not going to take much time. Another example where instead of one pole and 1, 0, we have 2 poles. And I'll make it even simpler by choosing the DC gain to be 1, so we're not going to have to worry about the DC gain. And the 2 poles to be identical. So I have 2 poles, both of them at negative 1 over tau. Okay? So what does that mean for the magnitude and phase? I'll be lazy here. Go back to example 1 and tweak that a little bit. So this was the plot for one pole, right? 1 over tau s plus 1. Now I'm looking at 1 over tau s plus 1 squared. So 2 of those multiplied. Therefore, both the phase and the magnitude need to be doubled, right? So that's why I'm not going to draw this all over again. I have to just change some numbers. And you can help me with that. So everything looks the same, except that this negative 20 becomes negative 40. Because I'm adding 2 of those, basically, right? Thereby multiplying by 2. This negative 3 dB becomes negative 6 dB, right? Everything else is the same. And the slope is negative 40 dBs per decade. Right? If I had 3 poles at the same place, that would have been negative 60 and so on. You're just multiplying. What happens to the phase? Each pole contributes a negative 90. You have 2 of those, so you go down to negative 180. So again, you're multiplying this by 2. So this becomes 90 degrees. This becomes 180 degrees. Rest is the same. Okay? Last example before the break is similar but slightly different. Now we're going to allow for complex poles. But we're going to cheat and we'll draw. I'm giving you the end of the story quickly, last page of the book. So we're actually going to pretend that the poles are real, even to draw the body plot for the complex case. And we'll see how we do that. What is our famous transfer function for a second order transfer function when the poles are complex? Remember that funny parameterization? Looks funny, but it's actually useful. S squared plus 2 times zeta times omega n s, omega n squared, and we put an omega n squared here as well, the purpose of which is to make sure that h0 is 1, right? When you set s equal to 0, it's omega n squared by omega n squared, so it's just 1. So we discussed that last time. The poles, or we intended to discuss that last time, I guess, are on the semicircle with radius omega n. They are complex conjugate when c is less than 1. As c becomes smaller, they go closer to the imaginary axis. As c comes closer to 1, they come closer to the real axis. Okay? And in fact, when c is equal to 1, what happens? This guy here, the denominator, forget about c, it becomes a perfect square, right? It becomes s plus omega n squared when c is equal to 1. So that means now you have two poles, two real poles, that are both at negative omega n. Okay? So how do I draw the frequency response of the body plot for this? No matter what zeta is, I pretend it's 1. Okay? It's pretty egregious as an approximation, but it's a good approximation if c is close to 1, so if you have a well-damped system. All right? So plot body as if zeta is equal to 1, which simply means that you're going to pretend that zeta is 1, so you have omega n squared by s plus omega n squared. Or I can just put it in this form by dividing both the numerator and denominator by omega n squared. I can write it in this form, s over omega n plus 1 squared. So that looks just like that, right? Aren't they the same? What is tau in terms of omega n? 1 over omega n, right? Same thing. So what we do then, if we are drawing a body plot for a second order term like this, we make a plot as if we're making a plot for tau s plus 1 squared, right? So that will be the last body plot you see in this lecture. Oh, what did I do? Actually, no. Here. Paste. Okay, so the second order term will give you a body plot like this. You go at 0 dB up until omega n, which is 1 over tau, right? And then you go down by how many dBs per decade? Squared, right? 40. So negative 40 dBs per decade. And then if you want to look at the phase, something very similar, you start at 0 degrees. You start at 0 degrees, and then you drop to negative 180 over 2 decades centered at omega n. 10 omega n. Okay? So is this a good approximation? Maybe. If zeta is close to 1, it certainly is a good approximation. If zeta is smaller, this obviously misses quite a few things. For example, if zeta is really small, if it's less than 0.7, you start seeing what in the frequency response? Resonance peaks. So in reality, in the magnitude, you would see some peak around here, right? This is completely ignoring that, although resonance can be a big problem in in practice. So in the last lecture, we had some body plots. I mean, the frequency response plots for this second order term, and they look like this. Okay? Our body approximation here is basically a straight line approximation to this, no matter what the actual zeta is. So it looks like that, constant, and then it goes linearly down. So this would be our body plot, and obviously it would miss all that stuff if zeta is small. All right? But that's how we do it, because body plots, again, are not meant to be accurate. They're supposed to give you a quick insight about what the frequency response is going to look like. So that way, if you practice your body plots, if I show you transfer functions, in 2 seconds you should say, oh, this is a low pass, no band pass, high pass. You should be ready for that kind of stuff. All right? Okay, 5-minute break, and then continue. What is this yawning and moaning and... Yes?
I think the last discussion, I was talking to TA about the stability of the LTI, the transfer functions. And you mentioned before that if the poles are located
All right, are you happy with Bode plots? Yes, they're easy, they're fun. Okay, so let's talk about, this is also very easy, so transfer functions of interconnected systems. So what if I take several LTI systems with individual transfer functions and connect them in series, parallel, feedback form, and what happens of interconnections? First, let's look at a parallel interconnection. So LTI system whose impulse response is H1, another LTI system whose impulse response is H2, and then we add them up. Same input goes to both, and the sum becomes the output. All right? So clearly y of t is the sum of the two branches here. The first one gives us H1 x convolution of t. The second one gives us H2 convolution x of t. And from the distributiveness of the convolution property of the convolution, the distributive property of convolution, okay, now I think I got it right, we get this. All right? So essentially, these together works like an impulse response, which is H1, H2, which is, we don't have to write these equations to infer that. So then what is the transfer function? You take the Laplace transform of that, and what do you get? From the linearity of Laplace transform, you'll get H1 of s plus H2 of s. So basically, parallel interconnections, you add up the transfer functions, just like you add up the impulse responses. Now let's imagine a series interconnection. LTI system 1 has impulse response H1, LTI system 2 has impulse response H2, and the output is y of t. So now I think it's the other property associative, or whatever it's called. I always mix those things up. But it's like we have one impulse response, which is H1 convolution H2, right? And what does this tell you about the transfer function? Well, convolution property of Laplace transforms. You multiply them, right? All right, isn't that nice? So instead of convolution, we just multiply transfer functions if they're in series. Very nice. The third important one, in fact, we'll get to use this quite a bit. I think next week I'll show you a little bit about feedback, how we design feedback loops and so on. So an important configuration interconnection that emerges there is the following. So you have x of t coming in. That's your external signal. Typically, a reference signal that you would like to follow. Perhaps a velocity profile that you want your cruise control to follow, for example. And then that goes into H1. And let's say in the feedback, we have H2. So these are the impulse responses of the corresponding LTI systems. And the output is y. All right? So then I ask you, what is the transfer function of this feedback loop? All right? That requires a little bit of algebra, but not too much. So we call this term here, the signal, that's the difference between these two, E of t. All right? So then clearly, the Laplace transform of E from the linearity property of Laplace transforms. So E of s is x of s minus the Laplace transform of this signal, right? What is that signal in terms of Laplace transforms? It's the output here, and the input to that H2 block is y. So the output will be H2 of s times y of s, correct? All right, so that's one important equation. Now, the next question is, how is E and y related? Well, clearly y of s is h1 of s times E of s. So take this E here, substitute here. You're going to get h1 x of s minus h1 h2 y of s. I'm dropping y, so I don't have to write s every time. So now you're very close to relating y directly to x. E is eliminated. E was an internal signal. We have gotten rid of it. If I move this term to the left, then I'm going to have 1 plus h1 h2 y, and that's equal to h1x. Therefore, y by x, which is our overall transfer function, is h1 over 1 plus h1 h2. We're going to use this a lot when we talk about feedback. Right? So the forward branch, h1, goes in the numerator, and then in the denominator you have 1 plus the loop transfer function, which is the product of h1 and h2. Okay? And naturally, when you do this, h1 and h2 themselves will be rational transfer functions. They'll have their own poles and zeros. When you apply this formula, things will change. So in the denominator, you'll get something quite different than the denominators of h1 and h2, right? That means the poles of the system will be moving around. That's one reason why we like feedback, because we can actually shape the poles of the system, closed-loop system, and that allows us to shape the transient response of the system, as we will see, right? Like I said, the most common application of this is in designing feedback controllers. So I'm going to go through that as a simple example. So when we do feedback, typical configuration is a reference signal coming in. And then an error signal generated by, so HP will be the system, the transfer function of the system that we actually want to control. Okay, it usually comes from first principles, physical principles, dynamical equations turned into transfer functions. And y of t is the output. So that's something we're interested in regulating with our feedback. If you're doing cruise control, that would be the speed of your vehicle. So how do you do that? You take y, you compare it to the reference. That's where you want to be. That's the speed you want to be at, right? R of t is that. Y of t is where you are actually at. So there's a sensor in this feedback. And then you compare them, and you generate E. Now you know why I called it E. Why? Error. How far are we away from the reference? So this system, usually the dynamical system we're trying to control is called a plant for historical reasons, because I think one of the early instances of feedback control was in chemical plants. Okay, plant coming from that. Okay, so our plant has an input. So there is something that we can tweak. That could be the throttle opening in the cruise control example, right? That we can adjust. The question is, how do we adjust that? Well, how is what lies in between these two arrows. I look at the error. Looking at the error, I have to decide what to do with the throttle opening, right? So that's what we call a controller. And we'll be talking about how that block should be designed in such a way that the resulting feedback loop gives us a stable system. Things don't explode. In addition, has nice transient properties. It converges quickly, so the output Y follows the reference rather quickly. So there are several design criteria. Of course, we'll talk about some of those. Not in great detail, obviously, because we don't have that much time. But if you want to learn more about this line of work, you would take 128 in the spring. All right, so then the question is, if I want to understand the transfer function from R to Y, what would it be? Well, the general answer for this configuration is here. If in the feed forward I have H1, in the feedback I have H2, then the transfer function is H1 by 1 plus H1 H2, right? Now, in the feed forward here, I have two things. So I look at the product of them. So HC, HP goes in the numerator, because that's what's in the feed forward. And what goes in the denominator? 1 plus the product of all the transfer functions in the loop. But there is no transfer function in the feedback, right? It's just a unit line, right? It doesn't multiply by anything. So we get, again, HC of S, HP of S. So that's the overall transfer function. That means Y of S would depend on R of S, the Laplace transform of the reference signal in this fashion. Okay? Again, a lot of control is about designing this HC so that the overall transfer function has the desirable properties, right? For one thing, we would want it to be stable. Again, we'll talk about these, but just a little preview. We would want this transfer function to be stable. What does that mean for the poles? Poles have real parts that are negative. And another thing we would typically want is when we look at the frequency response that comes from this transfer function, which is, of course, HC of j omega, HP j omega 1 plus HC j omega, HP j omega. And note that this is well defined because we are stable. Remember, stable means that the imaginary axis is within the ROC. And being in the ROC means that the Fourier transform exists, right? So this is actually a well-defined frequency response. So ideally, we would design this in a way that it's as flat as possible if our goal is really tracking. Okay, so you want it to look 1 for as long as possible. Why? Because I want my Y to look like R, right? Typically, we can make this happen for low frequencies. But if R is moving like crazy, you know, it's very hard to make Y follow it exactly, right? So what happens typically, I'm just giving you a preview without any proofs or derivations now. What will happen is inevitably the frequency response will start rolling off. Just comes from the fact that the plant itself will probably have a roll-off. It will not transmit high frequencies. Therefore, we can't expect that from the closed-loop system either. So, you know, one of the design criteria is to make this last, you know, this range of 1 last for as long as possible. When you look at things in the frequency response, there are actually very interesting design tools and very powerful design tools that people in industry use. They call it sometimes loop shaping because one interpretation of what you're doing with feedback is really shaping this loop. There are usually conflicting criteria. You would like this to be 1 for as long as possible, but keeping that to be 1 also makes you vulnerable to noise in your measurements and disturbances that are acting on the system. So therefore, typically people will say, well, I want my frequency response to be close to 1 in this range, and then I want it to drop after a certain frequency range because that's where noise starts becoming dominant. Okay? All right, so we'll talk probably not about loop shaping, but at least we'll learn how to manipulate transfer functions and how to evaluate stability of the feedback and things of that sort. Right? And move on. All right, so, you know, this is the first time I'm teaching 120 since 16 was introduced. So I'm adding some things to make the connectivity stronger. Bodhi, in the past, I didn't make a big deal of. I assumed 20, which was the predecessor of 16, did it. I don't even know if they did it or not, but I assume they did. But now in 16, we do these state space form of differential equation models. So in this course, so far in 120, we've dealt with linear constant coefficient differential equations that look like this. You look at the nth derivative of n of t, some coefficient n minus 1 times the n minus 1th derivative of t, a0 y of t, and then you have some x terms on the right-hand side, potentially some derivatives. I'm just writing a simple cartoon of that, right? in state space form, we don't have higher order derivatives. Instead of looking at higher derivatives of a scalar output, we instead generate a vector whose dimension is n. And with that vector, we don't take derivatives more than once. Okay, so that is a give and take. Instead of dealing with the nth derivative, you say, no, I'm not going to take more than one derivative. But instead, to pay the price for that, I'm going to generate a vector instead of a single signal y. Right? So this is the standard form, I would say, of differential equations, constant coefficient linear differential equations. State space is slightly different, although it is possible to go from one to the other. And that was the subject of 16. I'm not going to go into those again, but I'm going to remind you of what a state space looks like. So in state space, we have a vector z of t. In 16, this may have been called x. Okay, and maybe the input was not x then. Okay, but that's fine. So this is our state now. And it has n entries in it. That's called the state vector. And in circuit examples, this is typically inductor currents and capacitor voltages. And then this evolves according to its first order differential equation, but a vector differential equation because z is a vector, right? So we look at d by dt of z of t. That means take the derivative of each entry in this vector. So z1 to zn, you're looking at the derivatives of all of those. It is a matrix A times z of t. What's the dimension of this? dz dt has the same dimension as z, right, which is Rn, right, which is an n vector. So both the derivative and z are column vectors. So what must A be? A matrix that is n by n, if z has dimension n, right? And then we're assuming x is a single input, scalar. So we're going to have a matrix here multiplying x of t, and what should be the dimension of that matrix be? It has to take the scalar x, blow it up to an n vector. So n rows and one column. Okay? So that's a state equation. So it's a vector differential equation. Now, if we want to relate it back to a differential equation of this form where there's a single output, right? Then that output typically depends on z, and in some cases also x. So we write y of t again as a function of z of t and d, and then you'll have corresponding vectors here, c and d. Very often this d will be 0, but in the most general case it doesn't have to be. So can you tell me the dimensions now, because y is a scalar. So x is an r. Why is it scalar? Because if I were to use this type of representation, the output is a scalar. So you have a single input and a single output, but an nth order differential equation. So instead we're writing this as a first order differential equation with vector that's n dimensional. That's the whole idea of state space forms. So the dimension of C should be, since Z is an n vector, 1 by n. So that's like an inner product of two vectors, right? And D is 1 by 1. It's a scalar. And like I said in most examples, it's going to be even 0, right? So that's state space. So you saw this in 16. When you look at this again, how do you feel? I'm teaching 16, so this is an informal survey. Do you feel like you remember this, or is it like, shoot, here it comes again? You remember that. Okay. All right. So let's say, so in one of, I think the last lecture, I said, you know, if I give you a transfer, if I give you a differential, I didn't mean to. There is no. Okay. Anyway, so if I give you, I thought I was highlighting, not erasing, but if I gave you a differential equation model like this, I said, what is the transfer function? And we took Laplace transforms of both sides, and we got it. It wasn't a big deal. In fact, it was the numerator contained coefficients from the right-hand side. Denominator polynomial contained coefficients from the left-hand side. It was fairly simple. Now, today, I changed the question. Suppose you don't want to deal with these high-order differential equations. You like state space forms because you took 16. And I ask you, well, what is if I give you this A, B, C, D, what is the transfer function of that guy? What is y of s by x of s? Okay, we derive that. And you should be able to. The idea is the same. Again, look at the equations. Take the Laplace transforms. What do you see? If I take the Laplace transforms of both sides of the equation above, what do I get? Derivative means multiply by s. Now, what is the Laplace transform of a vector function? It's the vector that consists of Laplace transforms of its individual entries, right? And I'm going to call that, since it's still a vector, so I'm going to call that z vector of s. Okay? I'll be a little more explicit. Z of t is really a collection of scalar state variables z1 to zn. Could be voltages and currents and things of that sort, right? So z, when I say z of s, I simply mean the Laplace transform of the first entry to the Laplace transform of the last entry. Okay? So obviously, the derivative property applies individually, so it applies to the vector as well. And the right-hand side is linear, so linearity of Laplace transforms preserves everything. And b times x of s. I do the same thing here. I get y of s, which is not a vector, it's a scalar. C times z of s plus d times x of s. Goal, the aim is to relate y to x, get rid of this intermediate variable z, right? How do I eliminate z? I have to work a little harder on the first equation to be able to eliminate z. See, this has z in it, this has z in it. So let's put them all on the same side. So it's going to be some matrix multiplying z of s equals bx of s, right? What goes in that matrix? A goes with a negative sign. There's s here, but s is a scalar. So to be able to compare it to A, which is m by n, I'm going to have to multiply it with the identity matrix that's m by n. So si minus a. So that means I can actually eliminate z and write it in terms of x. It's going to be si minus a inverse times b times x of s. Next, I take this, substitute it here. So what do I get? So y of s is something times x of s, and that something is going to be our transfer function. All right, I'm waiting. Plus d. All right? So simple. We found the answer. So if instead of giving you an nth order differential equation, I can give you a state space equation, ask you what the transfer function is. This is how you do it. So you look at your ABCD, do this inversion and multiplication. It will spit out a scalar function of s, and that is your transfer function. So that's the big summary. H of s is c times si minus a inverse b plus d. All right, that's it. We derived an important formula. So A is m by n. So the matrix in the middle that I'm inverting is m by n. C is 1 by n. B is n by 1. So that multiplication gives me a scalar. Right? All right. C is a row. Si minus A is a square matrix, B is a column, D is just a scalar. So when I multiply these two, I get a column, multiply it with the row, I get a scalar, plus another scalar. So it's a scalar. Okay? All right. So one question, though. I said SI minus A inverse. That makes an assumption about SI minus A. It's invertible. A matrix is invertible when it's, let's say, full rank. Right? Rows independent, they are all equivalent. Full rank, independent rows, independent columns, they're all equivalent, right? So obviously this will be well defined when SI minus A is invertible. That is, SI minus A has full rank. But now there are values of S for which SI minus A drops rank. What are those values of S called? Eigenvalues, or self-values in plain English, right? So for the eigenvalues, SI minus A is not invertible. So this is well defined when S is not an eigenvalue. Okay? But at the end of the day, you can still do this because you're typically doing this symbolically, right? You're not really putting a value of S trying to invert it, right? You do this symbolically, and when you do this symbolically, you get a numerator polynomial divided by a denominator polynomial. So when is that rational function of S well defined? Or when is it ill defined? At the poles, when the denominator becomes 0, right? So it turns out the denominator of S is equal to 0 when S is an eigenvalue of A. Okay, so they are both ill-defined for some values of S, and those values of S in one view are the eigenvalues of A, in the other view they are the poles of the transfer function. So an important conclusion from this is that the eigenvalues of A are the poles of the transfer function. I'll just write TF for transfer function. Okay? So we found two important things. First, we found the formula for H of S from the state space form. And then we saw that the eigenvalues of A are related to the poles of the transfer function in a very simple way. They are the same. Okay? All right. So you seem to be with me. Nobody's complaining. So let's look at a couple of examples then. And I'm not going to do any other new material today. Let's just work on some examples and make this concrete. Now, this is an example that I did last time, or the one before, I don't remember. It was an RLC circuit with voltage X of t, resistance R, L, inductance, capacitance C, and we have this loop. Okay? So what we did was we defined this to be what did we define to be the output? I don't remember actually. Was it the current? I think the current, right? Yeah, so we defined the current to be the current that flows to be the output Y of t. So we derived the transfer function from X to Y by first writing a second order differential equation for this circuit. It wasn't very pretty the way I wrote the differential equation. I wrote an expression for the capacitor voltage. We took the derivative again. So the nice thing about state space, and that's why you were introduced to state space with circuits in 16b, is because it makes all of those derivations of differential equations for circuits a lot more streamlined, okay? A lot more principled, so there's no razzle-dazzle, it doesn't come out. You don't just get a second-order differential equation out of the blue. So what we do is we name the inductor currents and the capacitor voltages to be our state variables. So let's do that. Let's call this voltage Z1 and this current to be Z2, and you obviously see here that Z2 is going to be Y at the end of the day, right? Okay, so then we want to write differential equations for Z1 and Z2. We know how to write those because there are only two principles here. Capacitance times the derivative of the voltage is the current. Inductance times the derivative of the current is the voltage across the inductor, right? So these two principles are enough for writing differential equations for Z1 and Z2, and then they need to be related through KVL and KCL types of arguments. Okay, so let's start with Z1. So the equation is C times d by dt Z1 is what? Z2 is the current, but we already know it's Z2. Already here we use the Kirchhoff current law because it's the same current that's flowing through both, right? Okay, and then for Z2 we have to write this equation. L times d by dt of Z2, that is the voltage across this inductor, right? Now I use K. Some people don't like circuits. Now we use the KVL around this loop, right? So what is this voltage here across the inductor in terms of the other voltages? It is X minus this voltage, which is R times Z2, right? And then this voltage, which is Z1. Okay? So we are very close to having our desired state space form. State space meant d by dt of Z1 of t and Z2 of t equals a matrix to be determined, a 2 by 2 matrix A, that's our A, times Z1 of t, Z2 of t, plus a column vector 2 by 1, which we call B times x of t. All right, let's fill them in. So the first row will come from the Z1 dot equation. And this tells us Z1 dot is 1 over C times Z2, right? No Z1 in there, so the first entry here is 0. And here we get 1 over C. You all agree with this? All right. Now let's look at this one. This is going to populate the... Oh, and also no X appeared, right, in the first equation. So a 0 goes here as well. Now these three will come from the second equation, right? Z2 dot will be 1 over L times whatever you see in the right-hand side of that equation. So what is this first entry then? Minus 1 over L, because that's what you get in front of Z1. For Z2, you'll get minus R over L. And for the input, you'll get 1 over L. All right. So that's the first part of our state equation, right? Next, we need an equation that relates the output to this state. So what is y of t in terms of the states? So y is Z2, right? So you just select 0 here and 1 here, so it picks Z2, right? That's it. So that's our C. I'm going to call it C bar. Why? Because C was used here for the capacitance, so we don't want confusion, right? So this C is the C in the previous equation, A, B, C, D formulation. So D is 0 because no X appears in Y. All right, so if I ask you now the transfer function, our formula would be C bar is I minus A inverse B. So given the form of A, Si minus A is going to be S00S minus A, and A was 0, 1 over C, minus 1 over L, and minus R over L. So when you do the subtraction, you're going to get S, 1 over C, 1 over L, and S plus R over L. Okay? And then you need to invert this, right? So what's the inverse of a 2 by 2 matrix? What's the trick? Whoa, good job. Like a prayer, huh? So S plus R over L. Wait, what did I do? Oh, here. Yes, okay, thank you. S, and that becomes positive, and this becomes negative, right? And then, of course, you divide by the determinant. The determinant is going to be the product of this and that. That is S squared plus R over LS minus the product of these, which is plus 1 over LC. Okay? Now, C bar, remember, was 0, 1, and B was 0, 1 over L. Is that it? So when I multiply this guy from C bar from the left and B from the right, I'm actually going to pick only one value, the 2 by 2 entry, right? This one, because multiplying with this will pick the lower row. Multiplying with this will pick this column, so the intersection is S. So, and then we have this factor 1 over L. So we get 1 over LS in the numerator and S squared plus R over LS plus 1 over LC. Okay? Now, this here, what went in the denominator, which is the same as this, it really is the characteristic polynomial of A. And remember, roots of that characteristic polynomial are the eigenvalues of A. That characteristic polynomial appeared as the denominator of our transfer function, which makes sense because we just claim that the eigenvalues are the poles. That's because the characteristic polynomial becomes the denominator of our transfer function. So I can simplify this. If I multiply everything, both the numerator and denominator by L times C, then this looks prettier. So L goes away, you get CS. LCS squared plus RCS plus 1. And that's exactly what we derived last time without the state space form. Naturally, they should match. Right? Yes? Makes sense? Everything is connected. So I want to make some effort in what remains of this course to connect things up. Huh? Oh, it happened in my head. So I said I'm multiplying with this, therefore I'm picking up the row here. And then I'm multiplying with this, therefore I'm picking up the column. That's why I circled S. Yeah, sorry. Yeah, S. And then there was a 1 over L that came joined S. Yeah, be more detailed than me when you're doing homework and exams. So how many of you here have not taken 16 or otherwise been exposed to circuits? You. Anyone else? 2. Okay. Okay, so what's your background? Chemistry. You can actually come up with cool examples in chemistry. Mass action kinetics. It gives you nice differential equations. Yeah, if you had something like A goes to B and something like that, it actually gives you. I could improvise one for you, but I'm not sure. I'm worried I'll mess it up. Okay, let me try. So, like something goes to something. What's your favorite example? Don't say A plus B gives me C. That's not good, because then the mass action kinetics will give you products. So you don't want that, because it will give you a nonlinear differential equation. I want linear ones that I can play with. So pretty much, I don't want to say A, B. What other letters do you guys use? X, Y, for chemicals? Like H2 goes to 2H. I don't know, something like that. Okay. Okay, I'm really trying hard for you, but let's find some letters. P goes to Q. How is that? P goes to Q. Okay? P is a chemical. It becomes Q at a rate given by K. All right? So typically what is done is you look at the concentration of P. Okay? That bracketed notation denotes the concentration of P. And what's happening to P? P is just disappearing at a rate that's proportional to K and its concentration, so it's going to look like K times P. Okay? When P is disappearing, Q is appearing, right? At the same rate that P is disappearing, so you're going to get d by dt Q, right? So that's going to be, again, K times P, right? Because what's driving the reaction is the presence of P. As long as there's P, it's going to keep turning into Q, right? Does that make sense? So if I call this Z1, my first state variable, and this Z2, this again is Z1, and this is also Z1. Okay? So, and obviously there's no input, nothing, but just to give you a little flavor of state space equations, okay? So then I write d by dt z1 of t and z2 of t. So what goes in the matrix? So minus k goes here, multiplying z1. In fact, there's no z2, right? So the terms multiplying z2 are all 0, and positive k appears here, right? So that would be your A matrix in that case. Okay? Yes? All right, what else? What are their majors? I have an example for each one of them. Are there any mechanical engineers? Yeah? Okay. I mean, if you call this chemistry, this is a chemistry example. P goes to Q, right? And let's do some egregious simplification of mechanical engineering. So, how is that? Spring, what do you call these things? Damper, B, okay? And so I'm applying a force X. X of t is the force that I'm applying, all right? And let's mark the point where this is at rest when I'm not, the spring's at rest when I'm not applying any force. And the displacement from that, let's call it y of t. So I want to know the transfer function from the force to the displacement from rest. All right. So in this case, just like we pick inductor currents and capacitor voltages for circuits, for these types of mechanical things, you usually select positions and velocities to be the state variables. So I can choose y to be z1, and z2 would be its derivative. So that's the speed. So d by dt z1 of t is z2 of t, which is velocity. And then to find d by dt of z2 of t, of course, the derivative of the velocity is acceleration, and mass times acceleration is the net force, right? So what is the net force? It is x, but then there is some things pushing me back. The first thing that's pushing me back is proportional to the displacement, k times y, and y is z1, the displacement is z1. And then this is also pushing me back proportionally to the velocity itself. So it's going to apply negative b times z2 of t. Okay? So what does that mean? Well, that means I have my state equation. So d by dt of z1 of t and z2 of t okay, so we're going to put z1 here and z2 here, fill in the A matrix. All right. B matrix is going to multiply x of t, and then we're going to relate y of t to z1 and z2, and we already know how that works. We are not going to need a d, so I'm not going to write that. Okay, so let's fill it in. So z1 dot is just z2, so you get 0, 1, and no input, right? What about these entries? And? Okay, and output is z1 itself, right? So we pick 1 and 0, so the product is z1, right? So this is C. So you can on your own, I'm running out of time, do this multiplication. C times Si minus A inverse, multiply with B, that's going to give you the transfer function. You're going to get a second order transfer function. Ask yourself, this is not homework to be graded, but something you should do on your own. Ask yourself when these two poles are actually complex, when you have actual resonance, okay? And then try to write down these conditions. Of course, they will depend on M, K, and B. Try to connect with your intuition about, if there's, if the dashpot is, what do you call it again? Damper is not there. B is 0, then you're likely going to see oscillations. Or if B is small, you're going to see oscillations. So you should check these conditions for complex poles and even resonance to the values of K, B, and M, and try to build some intuition using that, okay? Especially if you're in a ME major. So since not all of you went through 16, let me be clear that, I do these things, and I do expect you, even if you didn't do 16, to sort of understand the mechanics of these state equations, A, B, C, D, right? And be able to apply this formula to get the transfer function. That much I will expect, okay? If I ever ask you to write state equations, I would give you the constitutive equations that you would have to put together. I wouldn't expect you to know KV